Hello and welcome for another thermodynamics video. So this one is going to be a video with a compressibility example. So obviously certain materials we are going to model as compressible, such as gases, specifically gases in this case. And so since gases are compressible, we are able to then model them using these compressibility charts, which is what we have, which I'll show the chart in a moment below. Okay, so what we're going to do is we're going to go off of the chart and then off of the tables to compare our results to see that actually because the chart becomes like a model of the ideal gas, then we can see that it's a pretty good model because it matches nicely with other data. Okay, so let's take a look. Determine the volume in cubic meters occupied by 2 kilograms of water at 100 bars and 400 degrees Celsius using data from the compressibility chart for part A and data from the steam tables from part B. Now we're going to see that it's going to take a little bit of work to get it off of the compressibility chart, but we'll get there. And then the last thing is compare the results of A and B and discuss. Okay, so we're going to look at the compressibility chart here below. So let's actually examine it. And on this compressibility chart, the thing I'm going to highlight here in purple is that the reduced pressure is on the x-axis, and then the compressibility factor is on the y-axis here. But we were given the pressure not as the reduced pressure, but as the just the plain pressure, the absolute pressure. Okay, so we're going to have to do a conversion here. In fact, to get the compressibility, because the compressibility here, this is by the way, this is figure I think A1 in your textbook. There are other figures beyond this that look similar to this one, and you just need to go to a larger reduced pressure. But in this case, we're not going to need to go larger than a reduced pressure of 1, because as you'll see, the reduced pressure that we use is actually going to be less than 1. Okay. So basically, what we're going to have to do is we're going to have to convert this to reduced pressure. And the way that we do that is we have this critical pressure, which we can find off of a table. In this case, this is from table A1. Okay, we're going to find the critical pressure and also the critical temperature of water, which is at the bottom of table A1 if you go in your textbook. Okay, so if we go there, so the reduced pressure is the pressure divided by that critical pressure. And notice that this is going to be a unitless quantity. The same thing with the temperature. It's going to be a unitless quantity, and it's the same idea. We divide by the critical in order to find this reduced. Okay. So going back and looking in the appendices at the very bottom of table A1, you find water, and the critical pressure for water is 220.9 bars, and the critical temperature for water is 647.3 Kelvin. But we have to be careful because we were given a temperature in Celsius, so we're going to have to convert that as well. Obviously, we just add 273.15 to that, and this is what we get. So basically, when we actually divide this out, we find that our critical, or that our reduced pressure is 0.45, and our reduced temperature is 1.04, because I'm dividing out those two quantities. Okay, so then we can actually go to our chart, and what we're going to find is that it's about 0.86 for the compressibility factor, Z. Okay, so if we go here, notice that this red line, this is at 0.45. That's the reduced pressure that we found, so that's nice. We can just go up this line, and then we have to find the curve for temperature up here. Notice that each of these is a different temperature curve, right? This one has a reduced temperature of 1, for instance, the one I just circled in purple there. And the next one has a reduced temperature of 1.05, so it's going to sit somewhere just beneath the 1.05 curve, because it's 1.04 is what we found for our reduced temperature. So going up here, you find, yeah, it's a little bit above the 0.85 line there. Okay, so we'll say it's 0.86. Okay, so the question asked for not the compressibility factor, of course, but for the volume in cubic meters. Okay, so we need to go from the compressibility factor to the volume, which we can do because we know this actually explicitly says the compressibility factor is equal to P times V, but that is a little lowercase v. That's the specific volume, not the volume. So we'll have to keep that in mind. But the P times V divided by RT. Now that R is not a molar R, so we're gonna have to keep that in mind as well. Which is what I'm going to show right here. Okay, so Z is equal to PV over RT, which obviously means that this nu here, is equal to Z times R times T divided by P, and we know that Z is 0.86, so we actually have all of these quantities. The note is that R without the bar is equal to R with the bar divided by M. Okay, so R with the bar is something that we actually know the quantity of. It's 8.314 roughly, and the units are in kilojoules. And the molar mass, this M here, this is the molecular mass of water, and we get that also from table A1, which it's right, you can read it right off the same table values that we found up here to get the critical pressure and the critical temperature. So we find that and substitute that in for M, which is 18.02, and then what we're going to want to get is obviously everything in terms of meters, and in this case in kilograms. So basically, first of all, we're going to convert the bars, so it's not just 100, it's 100 times 10 to the fifth, because a Pascal is a Newton meter. Then we're also going to have to convert the kilojoules that we found here to Newton meters as well. Okay, and obviously that's 10 to the third, because it's kilojoule, right? So 10 to the third Newton meters per kilojoule. So once you've gotten these all converted to their proper forms, the right to the proper scale, we multiply it out. So we have 0.86 times 0.8314, which divided by 18.02 times 673.15 divided by 100 times 10 to the fifth, and then multiplied by 10 to the third. And if you do that, what you should find is that you get 0.0267 cubic meters per kilogram. Okay, but that's my specific volume, so we need to convert it to volume, which is just multiplied by the mass. And if we go back to the beginning of the problem, the mass was 2 kilograms, so we just have to multiply by the 2 kilograms there, and notice that this was in meters cubed per kilogram, so that makes our lives nice and easy because it's going to obviously pop out cubic meters. And this is our answer. Okay, so what we found was, from using the compressibility table, we found, that we have 0.0534 cubic meters is the volume. Okay, and in part B it says do it from a table, so we can go to the steam tables, which is, in this case, table A4. And if you read off of table A4, you can find that at 100 bars and 400 degrees Celsius, that the specific volume is 0.02641 cubic meters per kilogram. So again, we have to do our conversion to get it into volume. This was obviously a lot less work than the compressibility factor, but we have to multiply by 2 kilograms, and we get 0.05282, which is pretty darn close if you look at these two values. This value and this value, they're pretty darn close to each other. So the compressibility is actually a pretty good approximation that we can use here. Okay, so all of this stuff came experimentally from gases, and in the end, it works pretty well even from other measured quantities in experiments. So that's all that I have for this video. Hope to see you again soon.